Thank you. Welcome. Welcome to Perimeter Institute. Welcome to Perimeter Institute, and welcome to our public lecture series. My name is Greg Dick. I'm the Director of Educational Outreach here at Perimeter, and it is a pleasure to welcome everyone, those of you here in the theater and those of you watching online. Today, the lecture will last approximately 1 hour and will be followed by some questions and answers. However, if you're watching online and you use hashtag PI Live, you can join in conversation with Dr. Damian Pope and a team of PI researchers, and they'll be willing to engage in conversation throughout the lecture. And then also at the end, if you have questions for our guest speaker, use hashtag PI Live in the Twitter feed as well to send in those questions, and I'll try to get to them as I can. And now, it is my pleasure to introduce tonight's very special guest speaker, Dr. Avery Broderick. Dr. Broderick is the Delaney Family John Archibald Wheeler Chair in Theoretical Physics at Perimeter Institute, and he is cross-appointed at the University of Waterloo. He completed his PhD at Caltech in 2004 and was a postdoctoral fellow at the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics until 2007, and then a senior research associate at the Canadian Institute for Theoretical Astrophysics until 2011. Dr. Broderick has broad interests in astrophysics, from how stars form to the extreme physics in the vicinity of white dwarfs, neutron stars, and black holes. And he has been deeply involved in the Event Horizon Telescope project, an incredible international effort to interpret horizon-resolving images of supermassive black holes, including the black hole at the center of our Milky Way galaxy. Tonight, Dr. Broderick will share with you that international collaboration and what might be on the horizon. Ladies and gentlemen, Dr. Avery Broderick.
Good evening. So before I get into what black holes are and what they look like, I always like to take a dive into black holes in our culture. I peruse Amazon and see what comes up when you search for black holes and you throw away everything that tells you what black holes are. And of course you get the movies. Some of them are beloved. Maybe that's why I work on black holes. Some are a recent phenomenon and some aren't so good. You get inspiration for music, and maybe I'm dating myself now. I couldn't help but notice one of the things that came up with Soundgarden's Black Hole Sun was a quote by Neil deGrasse Tyson saying, literally nothing in this song is correct, which is true. You get a lot of books. So here's one. I didn't realize black holes had a place in theology, but I certainly feel this way sometimes after lectures. I'll let you decide if that's also theology. Auschwitz is a pretty apt usage of the name, although maybe not my black holes. But then we get into things that make no sense, okay? Things like out of a black hole focus. But occasionally you get something that's absolutely spot on, like the black hole litter mat. I don't like cats. My wife is terribly allergic to them, but I almost want to get this. Or the black hole drum quieting sheet thing to keep your neighbors from filing noise complaints against you. Again, essentially right. Okay, so I think the point that I always come to after perusing the internet for where black holes are in our culture is that essentially people get it right. Black holes are things into which stuff goes, and then it doesn't come back out. But it turns out that it's not a terribly new idea. The first time somebody talked about objects in which light couldn't escape was actually in the 18th century. It was John Michell who noted that if you took Newton's theory of gravity seriously, that at some point things would have to be dark. And the illustration of this is, imagine throwing a baseball up. We all know what goes up must come down. You throw it up a little bit harder, it goes a little higher, a little bit faster, it goes even higher after that. How far out it goes is a function of how hard you throw it. There is a magic velocity, though. When you throw it faster than this, it escapes to infinity. For something like the Earth, that's 11 kilometers per second, so that's how fast you have to be launching rockets. If you're going to leave the surface of Jupiter, it's of order 60 kilometers per second. for the sun's 600. And what John Mitchell said was, what if you made that the speed of light, which at the time was known to be finite? Then you'd have an object from which even light couldn't escape. And he had this prescient quote that essentially says there would be these things that you wouldn't be able to see directly, but you'd only ever see through their influence on neighboring bodies. And interestingly, this is one of the main tools we use in astronomy to find all kinds of dark things, not just black holes, from planets to neutron stars and white dwarfs, but also black holes. So John Mitchell got a key element of astronomy right there. Of course, that's not our modern understanding of black holes. Our modern understanding of black holes comes from these two gentlemen. We have Einstein writing out equations from general relativity on the board. Clearly, this is staged. He looks slightly scared. We have Carl Schwarzschild, who gave us a Schwarzschild solution, which was the first non-perturbative solution to general relativity, and was the first black hole solution. And in it, we have a similar idea that there is this dark object, but there are some important differences. We can imagine having a light bulb shining at some distance from the black hole horizon. And light will be bent around by gravity. Some light will escape, others will be trapped. And as we move this light bulb down towards the black hole, more light becomes bent towards the horizon itself and is lost. And as we cross the horizon, everything is bent. And this differs from John Mitchell's idea in the sense that the light doesn't move one step outward before it goes down the throat of the black hole once you're inside the Schwarzschild horizon, once you're inside the event horizon. So how do you make a black hole? Well, it turns out it's really just a matter of size. It's a matter of making things compact enough. If you look at something like the sun, this is roughly a logarithmic scale in radius, 700,000 kilometers, and I were to squeeze that down to 30,000 kilometers, or 3,000 kilometers, I would get a white dwarf. It's just the next stable state of matter. And at some point, if I were to squeeze that white dwarf down to 10 kilometers, something the size of the Waterloo region, it would form a neutron star, something supported by neutron degeneracy pressure, essentially a large nucleus floating through space. But if I were to crush it down to 3 kilometers, the size of the city of Waterloo, then I would have a black hole. And that's all I need to do, crush the sun to 3 kilometers. It's a matter of size. So for the sun, it's 3 kilometers. I could do the same thing to the Earth. That's 1 centimeter. You could do the same thing to me. That'd be 10 to the minus 15 proton widths. Okay? You could do it to the universe, but I'll come back to that. And yes, anything can make a black hole. The black hole doesn't care what it's made out of. You could do it with the sun, you could do it with a large star, the Earth, and me. And this was proven by, first, that these things must actually exist in practice, was proven by this gentleman, Oppenheimer. Before he was making bombs, he was asking, what's the final fate of stars? And showed that ultimately, stars like the sun, or much more massive than the sun, 30 times the mass of the sun, would no longer be able to support themselves. They would begin to collapse and at some point form a horizon and transition into a black hole. That this black hole solution that Schwarzschild had found wasn't some mathematical curiosity, but was in fact a realizable thing in the universe. This gentleman here, John Archibald Wheeler, for whom the chair I'm very honored to have is named, he spent a good part of his career proving that in fact there was no other stops after neutron stars on the way to black holes. That there was nothing else that would stop you once you had a massive enough object collapsing, no longer supported by nuclear fusion, it will end up as a black hole. Now from an astronomical perspective, black holes are engines of the universe, engines of electromagnetic industry. And one form we see them practically is X-ray binaries. This is a black hole that is orbiting a neighboring star and cannibalizing it. And there are a number of examples of these, characterized by how far away from their partner they are and how large the disk of material falling from the partner towards the black hole is. And you can find them in the X-rays. In fact, the universe looks different in every wave band. But here's a picture of Andromeda, and it shows a number of X-ray point sources. Most of those are X-ray binaries. But there's also another class of black holes, supermassive black holes, things that are not masses similar to stars or tens or hundreds of times stars, but something masses of millions, billions, maybe 10 billions. And an example, a prototypical example, is 3C273. This is a quasar. What you're looking at is not a galaxy. You're looking at a single black hole. It produces a luminosity of 10 to the 47 ergs per second. It could be as high as 10 to the 48 ergs per second. There are objects that are that bright. That's 10 trillion solar luminosities. That's one supernova every 15 minutes. Compare that to one supernova every century in the Milky Way. So these things are enormously luminous. In fact, it's so luminous it outshines its host galaxy by a factor of 100. There's also this funny little feature you see extended in the bottom of the image. That's not an artifact. That's really there. That's a jet. It's a relativistic outflow of material that originates down near the black hole itself. Here's an image of a similar feature in Cygnus A, another supermassive black hole, somewhere else in the universe, launching jets out large distances before they terminate in these radial lobes. And in fact, these things can get enormous. The largest radio jet currently on record has a distance or a separation between these radial lobes, these spots at either end, where this relativistic stream of particles slams into the intergalactic medium and stops, of 4.5 megaparsecs. The typical distance between galaxies like the Milky Way is 1 megaparsec. So this is intergalactic. And these jets are not without consequence. Here's a composite image that shows radio emission, optical emission, and X-ray emission from a galaxy cluster. In it, the galaxies are white. So everywhere you see a little white spot, that's a galaxy in the cluster. The red shows radio. The radio are the relics from these jets that we saw in the previous slide. This is what's left over from those jets streaming out. And if you look closely, and maybe you have to squint a little, you can see in the blue, which is showing the hot X-ray emitting gas, cavities associated with where the radio jets were produced. In other words, the black hole at the center of this galaxy cluster isn't just announcing its presence by launching relativistic jets. It's carving holes in the gas in the cluster about all the galaxies that surround it. It's modifying its environment. It's ruling the fate of those galaxies. So what about for physics? It turns out that black holes are especially timely now. They live at the nexus of a wide variety of physics questions, and one of the key reasons is black holes are simple. They're characterized by three parameters. If you give me three parameters, I know everything I need to know about the black hole. You give me its mass, its angular momentum, and its electric charge. Then I can characterize how gravity around it behaves. And I don't need to know anything else. And in practice, I don't need to know the electric charge. Just the mass and the angular momentum will do, at least for astronomical black holes, because the charges will short themselves out on short timescales. And that's actually quite a contrast with our daily experience, because most things we know are not so simple. For example, the rhinoceros and the SUV are similar mass, but they're rather different. The same thing is true out in the universe about us, where we have molecular complexes, stars, etc., a wide variety of things. In other words, the universe is complicated, but black holes are simple. Now, there are a number of ways, if you're interested in gravity, of trying to probe exactly whether or not general relativity or this Einstein's theory of gravity that leads to black holes is sensible. An enormous amount of progress has been made using terrestrial and solar system experiments. I would call these high-precision, weak gravity measurements. Some people might take umbrage to that characterization. They are extraordinarily high precision. But fundamentally, they are experiments where gravity is making a 1 in 100 million correction, or general relativity makes a 1 in 100 million correction to Newtonian gravity, or 1 in a million in the case of relativistic binary experiments. It's the Hulse-Taylor binary pulsar, where they watch two stars orbit fall in towards each other a little bit, each orbit, as a result of emitting gravitational waves. But it's still a 1 in a million correction to Newtonian gravity. But black holes are fundamentally different because they are a place where you have 100% modifications of Newtonian gravity, where the gravitational potential in dimensionless units is of order 1. Okay? And it turns out that there's one other place in the universe where that's true. That's the universe as a whole. If I plug in the mass of the universe in terms of its density, you can get that this thing is also 1. This dimensionless gravitational potential is also 1 when you have 1 hydrogen atom per cubic meter and a size of 10 gigaparsecs. That's the cosmos. I said we would return to that. The Schwarzschild horizon of the universe is about the size of the universe. Okay, that doesn't really mean the universe is a black hole. What it does mean is that if you want to do cosmology, you should study your general relativity. But general relativity is a fundamental part of cosmology. General relativity is the reason why we talk about 95% of the universe being something other than you and me and everything we see. Something dark, like dark matter or dark energy. That's making the universe safe for general relativity. Everything else in the universe lives between the universe as a whole, whether gravitational potentials of order unity, and black holes. In the middle, the gravitational potential in this dimensionless form is considerably less than 1. This is where we would be doing weak gravity tests. Okay? So this is the only other place in the universe where general relativity is making 100% correction to what you would have expected from Newtonian gravity. And there be dragons. We don't actually know exactly what should happen. So, a black hole is more than a horizon. I'm going to share with you a little bit about what black holes do to orbiting bodies and key features within their space-time. It's a standard undergraduate exercise. What happens if we take the sun and we replace it with a black hole? And the answer is, of course, absolutely nothing. The Earth will continue to orbit. It will get a little cold. But if we were to launch a satellite, or maybe we already had a satellite, and that's why it has solar panels, and send it down to study our replacement sun, our new black hole. As it approached the black hole, it would come in closer and closer on orbits that look like Newtonian orbits, out to about 9 kilometers. And when it crossed this magic point of 9 kilometers, it would fall in suddenly. It's the innermost stable circular orbit. That's because orbits around black holes are different than orbits around larger bodies. At some point, there isn't a stable orbital velocity that will provide the centripetal acceleration necessary to bend you around. And there's a fundamental reason for that that's built into general relativity. It's that kinetic energy also gravitates. So as this satellite tries to go faster and faster, so that its centripetal acceleration will match the gravitational pull, its gravitational pull goes up. And it falls in. So there's this empty hole around black holes characterized by this innermost stable circular orbit. Now, that doesn't mean that you can't imagine having circular orbits. That doesn't mean you can't imagine putting your satellite on an orbit, only that it wouldn't be stable and in a single orbital timescale would plunge in towards the black hole. Another important location is the photon orbit, when this circular orbital velocity would be the speed of light. And it's generally unstable. We're going to see the impact of that in images for the Event Horizon Telescope. Black holes also don't just pull particles around, they pull space-time around. So you can think of things moving in a flow. That flow is the actual space-time. And at some point, the space-time is being pulled around so fast that the particles themselves can't ever be stationary relative to people far away or observers far away. That is to say, they may think they're stationary, or they may even put themselves on an orbit, get out their rocket engine, and start going around the opposite direction, but they would have to go faster than the speed of light for them to look stationary compared to the stars far away. And that's this frame dragging, this dragging of space-time. And that's characterized by this region called the ergosphere. Again, something that ends up being important in the astronomical manifestations of black holes. In some sense, the ergosphere, it sounds kind of like an odd idea because we don't normally deal with, or we don't normally deal with the mass current elements of gravity. Gravity for us is something very much like electrostatics, very much like static electricity. And I think we've all played with balloons, and if you have kids, you rub it on their heads. But many of us have also built electromagnets, and this frame dragging is just the gravitational analog of magnetic fields being driven by currents. Okay, so we have this picture of black holes physically, a number of interesting locations in their spacetimes. We know they appear throughout the universe as manifestations in X-ray binaries, manifest as X-ray binaries, and manifested as active galactic nuclei, but mysteries abound. So the first is we have millions of these mini monsters floating around. X-ray binaries themselves are exceedingly special objects because the black hole has to be nearby a partner close enough to tear material off the surface. But there could be up to 100 million dark black holes floating around the Milky Way. And interestingly, there could still be up to 10% of the dark matter produced by black holes. Now, not black holes like the sun, perhaps, things that are mass is a millionth or less of the mass of the sun. These would probably be primordial black holes, something formed in the early universe. But there's this great question mark, and people are trying avidly to close off this region. But up to 10% of the mass in this dark matter could be these black holes. And then we have the monsters at the centers of galaxies, said millions to 10 billion suns. If we look out in the night sky, you can see Andromeda, M31. It has a black hole at the center of its core, about 100 million solar masses. There's also M32, Andromeda's smaller friend, and it has a mass of about 3 million solar masses. They're both the same distance away. M31 and M32 are in the same system. M32 is a dwarf galaxy that orbits Andromeda. Okay, so this isn't just a projection effect. This guy's much smaller than that and has a much smaller black hole. Here's M87, an object that will feature in our story a little bit later. It's the brightest and most massive component of the Virgo cluster. It lives at the center. It's a giant elliptical galaxy, and I've shown these two pictures to scale. Andromeda is much smaller than M87, and M87 harbors a 7 billion solar mass behemoth. So bigger black holes live at the centers of bigger galaxies. And they do this despite the fact that they are a tiny fraction of the mass. Okay, you might think, well, bigger things live in bigger things. That makes sense. But they're such a tiny fraction of the mass, how do they know how large the galaxy is? I mean, do you know how large the galaxy is, right? How would you feel it? Okay? This is frequently presented in something called the M-sigma relation, or black hole mass, bulge mass relation, that relates the mass of the region around the center of the galaxy and the black hole that inhabits it. Here's the black hole mass, here's the bulge mass. This is an equal line. The black holes are 3 orders of magnitude less than that, and yet strongly correlated, so they know. So that immediately raises the question, is how do they grow in such a fashion that they know about their host galaxy? How do they launch the jets that affect the growth of their host galaxies? And even, I've told you that these are industrious, I've told you that they're very bright, but are they black holes? And there's the fact that we have these two classes, up to 100 solar masses and down to 1 million solar masses, raises a third question that I'm not going to answer at all today, and that is, where is everything in between? Do these become those, or are they fundamentally different beasts? But we will get to answers, maybe not today, but we will get to answers. We stand at the precipice of a golden age of black hole astronomy. We have a large number of different observing techniques that are all converging on studying black holes in ways that have never been possible before. The most obvious of which is the opening of the gravitational wave universe, the detection of the subtle ripples in space-time caused when two black holes run into each other. There are now many events that have been published, and LIGO is a prolific black hole finder, if not incredibly inefficient, because every time it finds two, it quickly becomes one. There's also the era of multi-messenger astronomy. Just this past year, we heard about the IceCube neutrino detector detecting peta-electron volt neutrinos. So how much is a peta-electron volt? It's 10 to the 15 electron volts. That's 1,000 trillion times as energetic as the light you see. That's a mere trillion times as energetic as the x-rays you get at the dentist's office. It's just an exercise in superlatives. And they originate in again, these active galactic nuclei, these supermassive black holes. For the first time, they were able to identify the origin of one of these peta-electron volt neutrinos. But neutrino astronomy is not the only multi-messenger astronomy. There's also a number of different instruments, both ground-based and space-based, probing the universe in gamma rays, X-rays, optical, near-infrared, and we'll talk about the radio in a moment. Okay, and all of these are unlocking black holes in new ways that have never been accessible before. And the third is what we're going to talk about today, directly resolving event horizons. Now, I know this looks messy enough to maybe be a real image. It's not. We'll come to that, okay? But this is the point today. The idea that now we aren't going to get these unresolved pictures or spectral information about black holes, unresolved point sources, but we are going to, for the first time, be able to identify where around the horizon did the emission come from. But why is this a challenge? So, the characteristic scale of this image, from this side to that side, is the characteristic scale cast by the shadow of a black hole. So here's a diagram that shows what happens if I were to take a black hole and put it in a uniformly bright universe. Every photon or every ray trajectory that I could trace back in time so that it hits the bright universe is bright, but every ray trajectory I trace back that lands on the horizon is dark, and there's a characteristic size of about 5 Schwarzschild radii in angular units. So it depends on how massive the black hole is, and it depends on how far away it is. And that number is insensitive to most of the things that, or the parameters of the black hole, insensitive to the mass of the black hole, its angular momentum, and like we said, the charge isn't important. I said before that this unstable photon orbit was going to show up again. The shape of this circle is determined entirely by that unstable photon orbit. And so it is a generic feature of things with horizons. So where do the black holes in the universe stack up in this angular size? Well, we have the stellar mass black holes that are very close to us. These are the X-ray binaries. I said there were of order 100 million of these floating around, but we know of order 20. Remember, those are the ones that are eating their partner star. The size of their shadow cast on the sky is somewhere around 1/1,000,000,000 of a degree. That's a little small. The black hole at the center of the Milky Way is about as far away as these stellar mass black holes, right? We see 20 stellar mass black holes in the galaxy. They're going to be spread roughly evenly through the galaxy. Okay, so it makes sense that the galactic center is about as far away, but it's also a 4 million solar mass black hole, so it has an angular size of a whopping 100 millionth of a degree. Next on the list is M87. We already saw M87. That's in the Virgo cluster. That's 17 megaparsecs away from us, which for a black hole of 7 billion solar masses is practically next door. It's like living down the block from Bill Gates. That's also 100 millionth of a degree. M31 is a little bit smaller, factor of 3 or so. There's a whole slew of supermassive black holes, AGN, that live between 100 billionth of a degree and 100 millionth. Something that I found pretty exciting was a couple years ago, there was this new ultramassive class of black holes that was discovered. A black hole is 20 billion solar masses. Nobody quite knows how you make a 20 billion solar mass black hole, or even if that's the limit. But this thing, NGC 1277, appears to be such a thing, and it's 77 megaparsecs away, which gives it a singular size, third on our list. So the number third target wasn't even known until a couple of years ago, but I don't think it's radio bright, so we're out of luck. Okay. The galactic center, or Sagittarius A star, as we call it, and M87 are the two top contenders on this list. And in units that are easier to say, there's 55 microarc seconds, or 40 microarc seconds. Okay, so an arc second is 1/3600th of a degree, and a microarc second is a millionth of one of those. So it's 100 millionth of a degree. How small is that in practical terms? If we look from Waterloo on the other side of the Earth and try to read the small writing on the dime, not see the dime. Anyone can see the dime. We want to actually read the dime. Look at the small writing on the dime. That's what we're talking about. Or as we enter this new space age, it's like watching the puck in the hockey game on the moon. I don't know about you, but I can't see the puck in the hockey games on Earth. But that's what we're talking about. That's 100 millionth of a degree. And there are fundamental limits that make it difficult to do this. Okay, and the chief one is diffraction. The diffraction limit is caused by the wave nature of light. And you don't need light necessarily to see it. Here are water waves. And you can see as the water waves approach and impinge upon these two islands, they generate these hemispherical waves propagating outward. Your ability to know what direction the water waves coming in came from is determined by how far apart these are. How large is the flat piece in the middle, right? If you're sitting here, you might have thought the light came, or the waves came from that direction. Over here, came from that direction. On your way home tonight, you can verify that this is a real thing. Just look at the street lights. In this picture, the street lights have this hexagonal pattern. Those are the diffraction spikes caused by the aperture of the camera. If you look at the street lights, you're actually measuring the shape of your pupil, which is kind of fun. That's how I determined I needed glasses. So that's what happens when you're a physicist. You ask your wife, Does that look double to you? And why are you staring at the streetlights? Okay, so if I look at things with my telescope, I'm a proud owner of an 8-meter reflector. I take my kids out every time that it's clear at Waterloo, which is unfortunately rare, and look at the sky. But if I take my instrument out, my diffraction limit comes down to the wavelength I observe at divided by the diameter of my telescope is 600,000 microarc seconds. So I thought that was pretty awesome, but it's also underwhelming for the prospect of measuring black hole horizons. So I'm not doing this in my backyard. We can move up. Here's the Sloan Digital Survey, Spectroscopic Survey, SDSS. They have a 2.5-meter telescope at Apache Point that they use to do their great work. There's also the Hubble telescope. If you wanted something more exotic, it's also about 2.5 meter diameter dish. Their diffraction limit, observing in the optical, is about 2,000 times what we need to see the horizon of a black hole. At some point, the James Webb Space Telescope will go from looking like this to looking like that. That is in space. And as wonderful as that is, it's still 600 times too low resolution. Modern cutting-edge Ground-based telescopes, 10-meter class telescopes, are in fact diffraction limited thanks to adaptive optics, which is an amazing technology where they're able to correct for the twinkling of the stars, correct for the aberration in the atmosphere. And you can tell that they're adaptive optics, that they're diffraction limited, because you can see the little diffraction patterns, the little circles, airy patterns around the stars until they clean them up, remove them, and pretend they didn't exist. These things are 500 times too low resolution. Even the 30-meter telescope is 100 times too low resolution. We need the 5-kilometer telescope, which maybe is in the next funding package. But there's another way. We're going to use another wave property of light and do an interference experiment. And so I'm going to remind you how the double slit experiment works, and I'm going to show you how we can turn that into a telescope. So imagine we have our light bulb shining on 2 slits. We know that that's going to produce an interference pattern. And why does it produce an interference pattern? Because the light follows the 2 trajectories to the 2 slits. Okay, and where the path is the same length from the light bulb, I'm going to get constructive interference. But where one path is half a wavelength longer than the other, I'm going to get destructive interference. Okay? And then if I move over a little bit further, it'll be constructive again and then destructive, and so I get a fringe pattern. Okay? If I move the light bulb, the fringe pattern moves. And it moves by an amount that's determined by how much the distance from my light bulb to my 2 slits is different from one slit to the next. As I move it more, the fringe pattern moves up. Okay, so you might imagine making a telescope where you measure the fringe pattern and you infer the source position. There is a complication, because if I move the light bulb far enough, and it turns out far enough is our diffraction limit again, lambda over a distance, then my fringe pattern matches up with where it was before. Shift it over, but I can't tell that. Okay? But the interesting thing about this angular scale is that it isn't lambda over the size of the slit, it's lambda over the distance between them. So it's a different distance. Now, the fact that I have this degeneracy means that I can't really tell the difference between this light bulb and this collection of light bulbs. So the price I'm going to pay for trying to do this experiment where I measure the fringe pattern and infer something about the structure of the source is that I get something about the structure on scales of lambda over u, wavelength divided by the distance between my slits, not the size of my slits. So I get some information about that. Formally, what am I getting? I'm getting information about the Fourier mode, the Fourier wave mode of my light bulbs. Okay? And as I go back, the fringe pattern moves again. This is exactly what radio astronomers figured out half a century ago. And when you see things like the Very Large Array in Socorro, New Mexico, this is what they're doing. Okay? The distance between slits is the distance between telescopes. Each telescope is itself a slit, and it's measuring the wave at that position, the radio wave incident from the astronomical source at that position. And you need a lot of telescopes to do this because you need to fill in the structure on all the different scales of the image. It's not enough just to have one pair. Then you can't tell the difference between a comb of light bulbs and a single light bulb. But if you have a large variety of different pairs, each pair can give you one of these interference experiments, and you can fill in all the information in the structure on all scales of the source. That is to say, the combination of all these telescopes is like filling in a mirror. That's the size of the separation between the telescopes. And the way you do this experiment is you measure the electric field of the incident radio wave at each telescope. You then go to a big computer and you combine them and run the second half of the interference experiment, where they propagate from the 2 slits to the screen. Look at the fringe pattern, okay, measure the brightness of the fringe pattern, and then you repeat this process for every pair. So how big can that distance get? Okay, things like the VLA gets to a few kilometers, maybe 60 kilometers. But you don't have to stop there. You could imagine building something the size of the Earth. Because now we don't have to build a single dish. We don't have to build a 5-kilometer telescope. Okay, we just have to put two telescopes 5 kilometers away from each other. And you can put them 10,000 kilometers away from each other. And this is the Very Long Baseline Array. So this is a dedicated instrument to exactly this endeavor. The angular scales that it can access, again, is lambda divided by the size of the longest baselines. In this case, that's 1 centimeter divided by 10,000 kilometers, the diameter of the Earth. That's about 200 microarc seconds. So now we're within spitting distance. How do we improve this? Well, we have two choices. We can make it bigger. Making the Earth bigger is very expensive. People do it. It's called putting satellites out there. But they're expensive. We can move towards shorter wavelengths. If we move towards shorter wavelengths, we decrease the top number. You go down by an order of magnitude, we're in business. And that's what the Event Horizon Telescope is. It's a version of the Very Long Baseline Array that operates at millimeter wavelengths instead of centimeter wavelengths. So why are we doing this now instead of 50 years ago? And the answer is the costs of sensitivity. Okay, the Event Horizon Telescope targets Sagittarius star, the galactic center, and M87 are quite bright in astronomical terms. There are 1 Jansky sources. There's a lot of micro Jansky sources in the universe, and people see them. So 1 Jansky sources are pretty bright. But how bright is that in practical terms? A microwave, if it's going to boil your water in an acceptable amount of time, has to be about 1,000 watts. Okay, you are producing 80 watts. I might be producing a little bit more than 80 watts right now. The black hole at the center of our galaxy, emitting in radio, it actually peaks at a millimeter. So this is its peak luminosity as it hits the Earth in a dish that's 10 meters, about 10 meters in diameter, 100 meter squared dish. Okay, produces 10 to the minus 15 watts. That's pretty small. So there's some lessons. The first is shut off the microwaves. We joke, but actually that mattered. You might have heard of fast radio bursts. There are people at Perimeter who work on this. It's an exciting field. There's a subclass of radio transients called peritons, and they noted that these peritons showed up suspiciously during lunch. They're microwaves. Okay? And the second thing is sensitivity. And sensitivity is, it's complicated by the fact that if you're going to make a detection here, you have to make it in the time scale over which the atmosphere is stationary, is not changing. Right? Stars twinkle because the atmosphere is constantly changing under the star, and so you're watching it dance across the sky. If you were to take an instantaneous picture of the star, you'll see a splat because it's being refracted through the turbulent atmosphere. Okay, the time scale over which the atmosphere changes appreciably at a millimeter is 10 seconds. At centimeters, it's much longer. So we really have to make a detection in 10 seconds. And we have to detect this thing that's really quite dim, 10 to the minus 15 watts. Okay? So how do we improve sensitivity? We make bigger dishes. Once again, that's hard to do. All of the telescopes in the Event Horizon Telescope were built for other purposes. We don't have control over that. And the second thing is to make bandwidths larger. What's the bandwidth? It's the region in frequency that you add up the light. So we don't add up the radio waves across the entire electromagnetic spectrum. It's not just radio waves. But near our peak frequency, we add up all the light within a range, and we can make that range bigger. And as we make that range bigger, we have more light, higher sensitivity. And we've pushed everything to 4 gigahertz. Okay? Why does that make it difficult to build the Event Horizon Telescope? Well, we're not just recording the power. This isn't like a camera. We don't just develop the film. We expose the film and develop it. Okay, we actually have to measure the electric field at the station throughout the observation. So think of producing an audio track instead of a single brightness measurement. And we have to do this 230 billion times a second if we're going to measure millimeter wavelength waves. Okay? It turns out it's not quite that bad. We really only have to sample sufficiently to uniquely determine within the bandwidth what the wave looks like. And that's about 8 gigabytes per second. But it's still 8 gigabytes per second at each station. That's about 64 gigabytes per second for the entire array. And for comparison, all of the experiments at CERN record about 25 gigabytes per second. So this is already a CERN scale problem. 225 terabytes per hour for a 1 week observing is 27 petabytes. Okay? Now, it's big data science, and it's expensive to get 27 petabytes of hard drives. And it turns out that this is one of the Moore's laws. Now, Moore's laws was about transistors on a chip, but there's all these now exponential things, and one of them is the cost per gigabyte has been dropping exponentially. And so now, because of this, it is possible to build a facility or build a instrument that can record with enough sensitivity to detect our sources at existing telescopes. And here's the pictures of disk packs lovingly produced by people in the collaboration. So here's a picture of the Event Horizon Telescope. It is a global array. This is what it looked like in 2017. We had 8 stations. 2 stations that were part of the array had unfortunately been decommissioned by 2017, but 2 new stations are coming online in 2019, so we're very excited about that. One way I like to characterize the Event Horizon Telescope is it's not big science, it's smart science. Now that feels less and less true every day. We have a large collaboration now, but it's smart science in the sense that we are leveraging billions of dollars of investment over decades in millimeter astronomy across the globe with a comparatively much smaller sum by synthesizing them all into a single array that can do this thing that none of the individual telescopes can do. Okay? So leveraging already available facilities. The Event Horizon Telescope operates at 230 gigahertz. It could operate at 345 gigahertz or 0.87 millimeters. We are working on the first demonstrations of that capability. And we do full polarization detections, and we can get robust detections to EHT targets in a second. Okay, so it does everything we need it to do. I want to emphasize that this version of the EHT, while magnificent, is not the first time we've done this sort of experiment. A prototype version of the Event Horizon Telescope has existed since 2007. It consisted of just 3 stations. Okay, so we're not getting enough information about any objects on the sky to produce pictures directly, okay, but we are getting horizon-scale information about objects on the sky. And with that, for more than a decade, we've been studying horizon-scale stuff around the black hole at the center of the galaxy, and for almost a decade in M87. So here's the collaboration. As of 2016, it's grown by leaps and bounds. Today, it's of order 200 people. There I am on the edge. So I need a diet. Of order 200 people, we have feet on 5 continents. We have the hard one. We have Antarctica. 13 partner institutions, of which Perimeter is one, and 36 affiliated institutions, of which the University of Waterloo is one. The big change in 2017 wasn't the jump from just 3 stations to 8, but was the important contribution or inclusion of ALMA. So ALMA is this enormous, exquisitely sensitive instrument in Chile. It is by far the most sensitive millimeter telescope on its own in the world today. And it serves as an anchor for the array. Because our ability to run this interference experiment depends upon the signal-to-noise ratios or the sensitivities of stations at either end of each baseline, we can get whopping detections from any station to ALMA. And we can use the information obtained from that to get detections from each station to each other. So without ALMA, the fringe patterns we can produce between different stations is marginal. And with ALMA, we get whopping, booming detections from these satellite stations, these other stations. So that's been the major improvement in 2017, is really the inclusion of this massive anchor. In April 2017, this full version of the Event Horizon Telescope observed for the first time, and we observed concurrently with a wide variety of additional telescopes, ranging from the gamma rays to longer wavelength radio observations. Okay. We observed both Sagittarius Star and M87. We have excellent detections, and you can see the importance of ALMA here. This is how well did we detect, or the number of detections is a function of how well we detected the fringe pattern. Remember that interference fringe? The baselines that don't have ALMA is peaked somewhere around a signal-to-noise ratio of 20. That's a 20 sigma detection. That's pretty good. The ALMA detections are up around 100. Okay, so ALMA's exquisitely important there. The analysis, unfortunately, takes time. The way you get 27 petabytes in one location is you mail it. There's no internet that will do it, so you have to physically collect them and bring them to correlation facilities. We have a correlation facility in MIT Haystack and one in Bonn. So these are large computers that are finishing this process of doing the interference experiment. Okay, you need a large computer to do this because you have to search through all the possible different positions of each station and the different atmospheric phase delays, which can be quite large at each site. So it is a long and onerous process that takes months. So we have to get them, that takes months. We have to run the correlation, that takes months. We have to calibrate it, that takes months. Then we realize we messed it all up and have to do it again, and that takes... But, success. So here's actual data that I'm allowed to show. It's not on Sagittarius Star M87. This is something called the closure phase, which is some version of the shift in that fringe pattern, or information about the shift in that fringe pattern, carefully chosen as a function of time. And the important thing is these points all have some value that's very clearly not zero by a large margin. The error bars on each one of these points is absolutely tiny in comparison to zero, the distance from zero. Now, the same thing's true for another source. Incidentally, that was 3C273, one we saw before. So what does a black hole look like? Well, I'm sorry, it's coming in early 2019. Maybe. So stay tuned. What does it look like in theory? Well, obviously it's a black hole. But if we put stuff around it, an accretion flow around it, it looks something like this. Here's a beautiful simulation by Hataka Shiakawa that shows material orbiting and falling in towards a black hole at the center. Here's a slew of other calculations of the images next to it, and they all show a characteristic structure. It has this crescent-shaped picture that's limb-brightened around the circle. Okay. The first feature, which is, I think, striking, is the hole in the emission in the center, the shadow. And that shadow is exactly that shadow that we saw before. Now I'm just showing it in terms of the photons that are hitting the horizon here. The photons have some different brightness because now they're integrating through luminous material. And for that reason, this shadow is not completely dark. There's emission in front because part of the surrounding plasma is in front of the black hole. The second thing that is obvious is this is the crescent shape. One side's bright and one side's dim, and that's because of the relativistic motions induced by the black hole. Remember, John Mitchell said we would find the black hole by its impact on, or its influence on luminous matter, and that's exactly what's happening here. The black hole is causing stuff to move around at near the speed of light, and we see one side Doppler beamed and boosted, makes it more opaque and much brighter on our one side, and the other side is receding, more transparent, much dimmer. And that's a characteristic feature of all these images. So what can you do with that? So in the remaining time, I'm going to breeze through a number of kinds of science or scientific analyses we're going to be doing or looking at in the next year with actual data. Give you an idea of the kinds of things you can expect this year and the next decade. So what's in a size? So if this looks suspiciously like the previous slide, that's because it is. But you see, I'm a theorist, so my ruler measures things in gravitational radii and gm over c squareds. I'm I'm also a theorist, which is why I use a ruler on my screen. We do better than that, but that's pretty good. What can you do with the size? Well, the first thing you can do is you can make a strong argument for the existence of event horizons, a strong argument that those supermassive things that produce all that luminosity at the centers of galaxies are in fact black holes. They have to be black holes. They have to be a thing into which stuff falls and doesn't return. And the argument is essentially the difference between a meteor and a meteorite. Okay? If I have stuff that's falling onto a central accretor, it's rubbing up against other stuff in this headlong charge towards the central object, whatever that is, and it heats and it shines, just like the meteor shines. Okay? If the meteor still exists by the time it lands in the ground, though, it makes a large divot. It's the impact luminosity. That's the excess kinetic luminosity it had that it didn't impart to light, it didn't lose to light by shining on the way down. And if I had accretion onto some object that wasn't a black hole, something where I could see its event horizon, see its photosphere, something like a star, you would see this impact luminosity. You'd see this heating of the surface of the star caused by the constant rain of infalling material upon it. Okay? So the difference between something with an event horizon and something that doesn't have an event horizon is whether or not you see this impact emission. So in the galactic center, you can look for that, and it turns out that naively, and I'll justify this in a minute, you would expect this emission to come out in the infrared. And if I were to make a picture of the black hole, the center of our galaxy, in the infrared, it's 2.2 microns, and add a luminous surface associated with this impact luminosity, at some point it pushes far above all the observed infrared limits. In other words, it's too bright. I said I had to come back to why did I think it was in the infrared? I could get all this impact luminosity out by making the surface large, making this object large. I mean, how do we know that the black hole at the center of the Milky Way is the same, or the object at the center of the Milky Way is actually the size of a black hole? How do we know that it's not 1,000 times as big as a black hole? And therefore, this luminosity spread out over a much larger surface and can be much cooler. It can be hidden in spots in the spectrum where we don't have good limits, big and cold. Well, the answer is the EHT already tells me that's not true. Right? The proto-EHT made these horizon scale measurements of the structure in the black hole at the center of a galaxy, and it is certainly not 1,000 Schwarzschild radii across. So big and cold is ruled out. Small and hot is how it would have to be. And if we had a surface, if we had a photosphere, if we had a place where we could see where the stuff went, we would see a bright infrared source, which we don't see. So in some sense, this is an argument along the lines of the dog that didn't bark. Okay, we see a signal, or we don't see a signal that we should see if it weren't a horizon, and you can wiggle yourself out of this if you really, really try, but usually it involves tooth fairies. My favorite was, I used to joke about how you could get around this by positing that the black hole was a wormhole that emptied into intergalactic space. But of course, if you start making that argument, then I think you've conceded the point. The black hole is by far the least crazy of the two options. But then Thibault Demore wrote a paper saying that. So if it's funny enough to make a joke, I guess you should write a paper. I pointed out that this was before gravitational waves. We made this argument in 2009, 6 years before gravitational waves. So before gravitational waves verified that there were black holes that were running into each other, we already knew that there were things that were black hole sized that had something that looked like a horizon. You can measure the size explicitly. You can do a better job than what I did before. And when you do that, you get a measure of this mass divided by distance, this angular size of the shadow. Okay? And you can use that to improve our estimates of the mass and the distance to the center of the galaxy. For Sagittarius A star, for the galactic center, that's a marginal increase. There are excellent ways to measure the mass and the distance to the mass of the black hole at the center of our galaxy and its distance. But for M87, it can be revolutionary. And that's because there are two ways that people measure the mass of M87's black hole. They both involve observing things that are orbiting around. and assuming that they're orbiting on Keplerian orbits. But in one case, people observe stars, and if you observe the stars, you think it's 7 billion. Other people observe gas, and if you think it's gas, the gas is orbiting around on this Keplerian orbits, then you get 3.5 billion. Now, I'm partial to 7 billion because that makes M87 bigger. But how do you tell? And I should point out that the uncertainties, M87's uncertainties are pretty good. It's a plus or minus 10%-ish. So it's 7 or 3.5 plus or minus 10%. And, well, they disagree. EHT can settle that. Okay? And that's going to have an important consequence for how material gets from the parsec scales, where you measure the gas, down to the black hole, where the EHT measures its mass. I can also interpret this mass measurement in a slightly different way. The Event Horizon Telescope mass measurement is really a measurement of what gravity does on scales comparable to the horizon. This other guy, this gold bar, it comes from measuring stars in the galactic center. So does the cyan blob. Okay, this is gravity out at thousands of source shield radii, tens of thousands, hundreds of thousands of source shield radii. And so this is measuring the mass of the black hole, or equivalently measuring its gravity at different locations. And general relativity is the theory that tells me how these should relate. And so even an approximate measurement of the mass of the black hole at the center of the galaxy is a direct test of general relativity, comparing what does gravity do on scales of the horizon compared to what it does on parsec scales. Now, in what follows, I'm going to talk a little bit about Sagittarius star and M87 in more detail. Just some quick facts about them. We said Sagittarius star was at the center of the Milky Way. I said it was 4.5 million solar masses. M87, center of M87, much further away, much larger. They're both very underluminous, but one thing that I think is important to the EHT story is that Sagittarius star and M87 are essentially the two sources you wish you had if you had only two sources. They're as different as they can possibly be in almost every other sense. Sagittarius star is the kind of mass of a typical black hole at the center of a typical galaxy. M87 is an enormous behemoth at the center of a very, very large galaxy. Sagittarius star is a point source in the radio. It doesn't show any evidence for any extended features or outflows. M87 has a powerful jet. Okay? And both of them are in a regime where we think we can estimate what the structure of the plasma around them looks like. And so that comes in mad, insane varieties. Mad sane came first, but it wasn't named that. The difference between mad and sane, these are both accretion flows that are very low density. Okay, the gas right around the black hole at the center of the Milky Way is still better than the best vacuums on Earth by a large margin. And as a result, it can't effectively cool. All the gravitational binding energy that's being liberated by the protons doesn't get turned into luminosity. And so it stays hot and thick and a big puffy disk. Okay? Knobs we can turn are the mass accretion rate. We can push more mass in towards the black hole. We can change the angular momentum of the black hole. And we can change how much magnetic flux gets accreted. So if I just had a hydrodynamic flow, or if I had a flow that had very tangled magnetic fields, so sometimes I would accrete a field that was going up, and sometimes I would accrete a magnetic field that was pointed down, and I wouldn't accumulate any net magnetic field, then we get this sane picture, this big puffy picture. But if I constantly feed it the same magnetic field, in this case down, okay, give it the same thing over and over again, then you generate a large amount of magnetic flux, which crushes the accretion flow right around the equatorial plane. And that's a magnetically arrested disk. Sane is standard and normal evolution. I guess somebody has to define normal. But, okay, these are the pictures that we have for M87 and Sagittarius A star. And they really depends upon just these three parameters, of which mass is just this overall governor. So really, black hole angular momentum and magnetic flux, these are the two things we might imagine are changing the story for M87, which has that powerful jet. Okay, so why are they different? Presumably the knobs. So does this picture work? Here's a picture from an analysis of taking those sorts of models and comparing them to the proto-EHT data over the first 7 years, so not up to 2017, up to 2013. They're different pictures in each case. It's hard for me to tell, and I'm right next to them. That's the picture I like to show because it's our best fit picture. It turns out that it gives a pretty decent story for the galactic center. The angular momentum implied, or the direction of the angular momentum implied for the black hole at the center of the galaxy, seems to align with the origin of the gas, the angular momentum of the disk of stars that blows material down towards Sagittarius star that dominantly feeds its accretion flow. So that seems to make sense. It's aligned with other features in the galactic center, which it ought to be aligned with, and not aligned with others that it oughtn't to be. So at least it hangs together, so this is consistent. Also, it hits the Goldilocks zone in polarization. I said the EHT can measure a full gamut of polarization. And if we look on very large scales, the galactic center has very little polarization, but on small scales it has a large amount of polarization, and the way in which you make that happen is by having an ordered magnetic field, but not too ordered. Okay, so it's ordered on your small scales, but it's not ordered on your large scales, and again, that's a natural output of this sort of model for how black holes feed. Okay, so if you believe that, you might then say, Can we change something besides one of those knobs? Can we change something about the stage on which the drama unfolds? And the answer is yes, we can violate this statement that the black holes only care about 3 numbers. We can add a number by hand, manually. It's not a solution to Einstein's theory, but it gives us a way to ask how different is the black hole that we have in the galactic center from a black hole as predicted by general relativity. And we characterize that by some parameter, which is 0 when general relativity is correct. And by making this non-zero, the image is distorted in different ways. This is what happens if you make your black hole more prolate or peanut M&M-y, more oblate, more regular M&M-y. Of course, you could do crazy things like add additional stuff around the black hole, light scalars in the universe. You can even get a Naboo starfighter. I wonder how long they spent trying to find that. A while back, we asked, well, what kind of constraints could you place on this? And we made this plot, and it's kind of dismal. This is the 1 sigma limit, that's the 2 sigma limit. At 2 sigma, every possible parameter, every possible value of how broken GR was allowed. So it was a proof of principle. A student of mine a number of years later produced this plot. He didn't know why I was so happy, but it was because all of a sudden we had some 2 sigma things that weren't allowed. But this is what the 2017 EHT observations in an ideal world will be able to do. Sub-percent constraint on just how non-GR-like the black hole at the center of the galaxy is. Now, in practice, it might be worse than that. This assumes that this model I described is the right picture. But if that's not true, then this changes. So, the rest of the stories I'm going to tell you are about variability. That first picture is going to be fantastic. We can't wait to produce it, analyze it, and distribute it. But I think a lot of the science that we're going to get out of the Event Horizon Telescope is going to happen not when we make one picture, but when we start making movies, when we go from images to cinema. And that's because each of the EHT targets, M87 and Sagittarius star, exhibit structural variability over a large variety of timescales. And each one of those kinds of variability tell a different story about its environment. Okay? So what I'm going to tell you next is about movies. So the first is jitter. This happens on time scales of decades. It's probing the structure around the black hole on tens of thousands to millions of Schwarzschild radii. And it's Brownian motion. Here's a picture of pollen grains suspended in fluid, and they all bounce around. And why do they bounce around? Because atoms and molecules are bouncing off the pollen grains, and sometimes you get more atoms or molecules from the left, and that pushes the pollen grain left, and sometimes you get a few more from the right, and that pushes it a little bit right. And this jitter is the thermal motion of the pollen grains constantly being bombarded. The size of the motion depends upon the mass of the molecules in your fluid, and the density, and so number density. So it tells you something about what your fluid is made out of if you knew the properties of your pollen grains. The same thing is true, let's start it again, of black holes at the centers of galaxies. Sagittarius star is just the right mass so that the stars in its vicinity, no, they're underneath, I apologize. The stars in its vicinity will cause it to jitter around on scales comparable to its, on scales comparable to its horizon scale, of order a microarc second or a few microarc seconds over years. So we can watch Sagittarius star wander. Now, the thing that makes this difficult with anything but the Event Horizon Telescope is that if I saw the bright spot of Sagittarius star move around a little bit, how do I know that's not just the fluff, the accretion flow, the shiny bit, which is much lower mass than the black hole? With the Event Horizon Telescope, we can see where's the shadow. We can watch the mass. And so you can use that to constrain how much and how massive the stuff is around the black hole, just like the pollen grains tell you about the fluid. Say something about the history and evolution of the nuclear star cluster. There's also another interesting mystery. I mentioned I wasn't going to say anything about intermediate mass black holes, but I can't resist. There are these population of stars down at the center of our galaxy. André Ghez coined the name the paradox of youth. They're all too young to be there, and they're all too big to have formed there. So where do they come from? And one possible answer is that they were bussed in, that you made a globular cluster out there, it fell in, and then deposited them in their current positions. But if you try that, the globular cluster falls apart at much larger distances than where we see these stars. You can fix that by adding an intermediate mass black hole, which holds the cluster together and carries it all the way in. But that means that there should be an intermediate mass black hole floating around with a period of order 10 years near Sagittarius star, and that would cause Sagittarius star to move around on the sorts of timescales we're talking about as well. The second example, as I said before, that the angular momentum of Sagittarius star looks like it's aligned with the source of its accretion flow. But it's not obvious that that should have been true. Okay, the stars that generate the gas that falls onto Sagittarius star have not dumped a large amount of gas on Sagittarius star over its lifetime. And so if it had an angular momentum that was pointed in some other direction, it could happily have been still in that direction. And if that were true, then this frame dragging we talked about early on would play an important role. There's something called the Bardeen-Pedersen effect, which causes disks to align with their black hole. The disk is coming in tilted at some other angle, but as it gets close to the black hole, the frame dragging causes it to line up so that the disk angular momentum is aligned with the black hole angular momentum. Okay? But for the kinds of big, fat, fluffy disks that we're talking about for Sagittarius star, for the galactic center, the story is a little different. The disk should, in unison, precess around. And if it precesses around in unison, we should see a secular variation in the reconstructed directions of the black hole spin. And the time scale for that's of order a year. We have some constraints on that, but one of the key things about those constraints is there are all these features which are associated with the fact that the EHT observes every April. And so everything that has a period of 1 year, if there was a precession that had a period of 1 year, we would have a hard time seeing it, and sensitivity. So that will improve dramatically in the near future as well, and tell us something about the relationship between the source of the gas and the accretion flow and Sagittarius star. M87 is also variable. It's variable on time scales of days to weeks. Here's a radio image at 7 millimeters at a centimeter, about a centimeter, that shows features moving out in the jet. If you try to track those features back to this little box that I drew here, this is the region being shown in the EHT image on the right. If we trace those back, we get very different evolutions, very different features, depending upon whether or not the stuff that we're seeing in M87's jet is being launched by the black hole itself or a consequence of an accretion flow around the black hole. Whether or not the black hole is playing the dominant role in launching these outflows that play this important, have this important impact at large scales, or whether or not it's an accretion phenomenon. Okay, so we can, in principle, observe one of these blobs moving out, which seem to be happening nearly all the time, and say conclusively where M87's jet originates from. And the last thing I want to tell you about is flares in Sagittarius star, in the galactic center. This happens in time scales of minutes. And so here's an infrared movie. You see Sagittarius star suddenly gets to be bright and then becomes dim. That happens once a day. Sometimes there are oscillations. Some people will swear they see them, others will argue with them. But it certainly does flare once a day. The origin of for those flares are not fully understood, but there's a natural explanation from something like the simulation from Takashi Akawa. Here we see a large amount of turbulence in the accretion flow, and when we have a turbulent magnetized medium, one of the things that happens is that you drive magnetic reconnection events. You drive solar flares. So you can imagine this sort of turbulent behavior will produce solar flares, but not on the surface of a star, in the middle of the accretion flow. And that's a good model. If it's not the model for flares, it's certainly a model for a good number of them. About 15 years ago, we first talked about trying to model these flares as hot blobs in the accretion flow. And the key element of modeling them as hot blobs in the accretion flow is that they're constantly being gravitationally lensed as they go around the black hole, and you can see the primary image, and you can see a secondary image associated with photons that go around the black hole and come to us. And the relationship between these two images tells us something about the structure of the space-time. Since that time, this sort of model has been dramatically improved. And now we don't have a blob that stays coherent, but a blob that's being sheared out. But it's the same story. We see features in the image associated with those different structures in the space-time. And the key thing that these sorts of transient features do is they separate out where the emission happens and when it happened. And so you can begin to talk about tomographically mapping out the space-time from each flare. The idea is something like this, where what it is this is angular momentum of the black hole as a function of flare launch radius. Okay? But what you should really read this as is space-time structure, something about the structure of the space-time as a function of radius in the space-time. This is CAT scanning space-times. And so with a handful of flares, we won't just know whether or not general relativity is consistent in the galactic center, but we will be able to say that, in fact, the structure of the space-time is exactly what Carl Schwarzschild says it was, or Roy Kerr says it was, or it's not. All right, so I've gone a bit over, so let me just finish by saying I think it's fair to say that the era of strong gravity has begun, and I think about this image a little bit like the pale blue dot. Right? So the pale blue dot, when Voyager looked back at Earth and sees it as a single pixel, reminds us we're all on this lifeboat together, and everyone you've loved, everyone you hated, was all in that one pixel. We're all one family. This picture, I think, is similarly resonant, but it tells us that there really are these monsters in the night into which things go, and they don't come out. Thank you.
Very good. Thank you. We do have time for a couple questions, so if you do have a question in the theater here, the microphone is right there, and I'll quickly jump right to an online question to get started. And this question is, do super heavy black holes move with the universe's expansion?
Do they move with the universe's expansion? They move with their galaxies. They are stuck to the centers of their galactic potentials. So in fact, one of the ways you might verify that a supermassive black hole is indeed a supermassive black hole is by ensuring that it's sitting down at the bottom of its gravitational potential. It will very rapidly lose its energy by sloshing the stars around and sit down at the bottom of the center. Now, galaxies, in large part, galaxy clusters are certainly tracers of the cosmological flow. So in that sense, they follow the flow. Yeah. But any one galaxy can be separated from the flow, right? The Earth and Andromeda are moving towards each other. We're not in the Hubble flow.
In the theater.
Hi there. Great presentation.
Thank you.
My question is, you keep talking about the stuff that gets ejected from a black hole. What is that stuff? And also, does it somehow propel the black hole through space, or like, what effect does it have on the black hole, if anything?
Right. So I specifically did not say what the jets are made out of because we don't really know. And it actually has quite a substantial impact on how you interpret them. They could be filled with protons, so ionic gas, right? Protons and electrons. That would make them very heavy. They could alternatively be almost electromagnetically pure. They're just giant electromagnetic waves flowing out that sometimes gets converted into a little bit of energy and electrons. But knowing exactly what constitutes those jets is one of the key questions facing astrophysics at the moment, and that affects then how much power you need at the bottom, what kind of processes you need down at the bottom to launch the jets, to get the sorts of radio lobes we see downstream. Now your second question, what is the impact of the jets on the black holes? In every instance that I am aware of, jets are symmetric. They don't look symmetric, okay, because they will be, one is relativistically moving towards you and looks bright, just like that looks bright when it comes towards you, and the other one will be moving away from you and looks dim. But if you see blobs move out, if one blob goes out front, one side, a counter blob goes out the other side. So I don't normally think about how it pushes the black hole around, but that's an interesting question. What kind of limit would that put on that?
Thank you.
Thanks. Let's go in the theater.
I'm not sure if this applies, but are wormholes and black holes similar or different?
Well, they're similar in the sense that both represent extremely curved spacetimes, right? And both can be constructed with an appropriate matter content and general relativity, but I think they're fundamentally different in that black holes are an inevitable consequence of gravitational collapse. They have to happen, which is a stunning statement, right? Because the matter collapses, forms a black hole. There's nowhere for it to stop. It goes straight onto a singularity. So black holes are, it's an admission that physics produces a thing physics doesn't understand it yet, right? That's why we have so many people who think about quantum gravity, quite rightly so. So we know that will happen, but there is no natural process that I'm aware of that will produce a wormhole. And I think you need exotic material to actually hold a wormhole open, which we don't know what would be. So in that sense, they're different.
Thank you.
And let's finish with one last online question. We all look up in the night sky and feel curious, but when did you first realize you wanted to study black holes and other mysteries of the universe?
Oh. When I was young, I would visit my father and we would watch Star Trek. And so I would see them go on these magnificent adventures, and I thought that was great. I want to do that, and Starfleet doesn't exist, so I do it this way. Yeah. Anyway.
Terrific. Ladies and gentlemen, Dr. Avery Broderick.